So I want to use this to introduce you to some equations that we're going to be using in the next few days. And this section is called work, power, potential, and kinetic energy. So first, the equation for work. Work is, in physics, defined as a force applied over a distance. So when we look at variables, we have work is equal to F times D. Thinking about units, a force is a Newton. The distance has to be in meters. And when we break that up a little bit more, remember a Newton is a kilogram meter per a second squared. So if I multiply that other meter, we have a kilogram meter squared second squared, and that unit is called a joule, and its abbreviation is a capital J. It's an energy unit. And we'll be doing some practice problems in class, and we'll be doing an activity, so if you're listening to this, be sure to wear sensible shoes tomorrow because we'll be climbing the stairs. Now, a new term for you is power. And power in physics is the rate at which you do work. So power is work over time. So power is a capital P, work is a capital W, and time is a lowercase t. Our units for power, well, first work is a joule, and time is in a second, and our power is called a watt, and that's a capital W, not to be confused with a capital W for work. And that's the rate at which you do work, is how much power there is. Now, a couple of other equations that are closely related to these two. One is kinetic energy, and kinetic energy is 1/2 mv squared. And on our equation sheet, we have it written, K is equal to 1/2, m is for mass, v is for velocity, squared. Let's look at the units for this. The mass has to be in kilograms, and when velocity is squared, we get meters squared over seconds squared. Does that look familiar? It's a joule, which is when you do work, you apply a force over distance, it's in joules, and so is kinetic energy. Our last equation is potential energy. And potential energy, you would think they'd use a P, but we used a P. That was for power. We're going to use a U. And U is for potential energy, is equal to mass times gravity times height. And potential energy is always with respect to the Earth. So we're looking at a special D. And so we have U equals mgh is the formula you will be using. Our units, again, mass is kilograms. You know gravity is meters per second squared, and height is going to be in meters. So you see how we have kilograms, meters squared, seconds squared? And yes, this too is a joule. So I'd like to use a video that's from Harvard, and I have the web address, and you can see it at multimedia.mcbharvard.edu. And if you cut and paste that web address in, I'll try showing it to you. We'll see what happens. And I think I go like this. back to this, and here's my rhino. And we're going to look at the exchange of potential energy and kinetic energy. So when something falls, it gives up potential energy and it begins to gather velocity, and that converts that energy into kinetic energy. So my rhinoceros, it says, based on its height above the ground, the rhino possesses gravitational potential energy. Off the rhino goes. It says, during the fall, most of the potential energy is converted into kinetic energy, and a small amount is transformed into heat as the rhino moves through the air. Notice how red he's getting? Oop. Upon impact, let me go forward, sorry. Upon impact, that energy, let's watch him turn red again. There he goes, that's the air resistance. So upon impact, the kinetic energy is converted into many energy forms, including heat, energy to make and break chemical bonds, such as the pavement fragments, and that potential energy is converted into a range of types of energy, but it's always conserved. The total energy remains constant. So tomorrow in class we'll do an activity with this, or maybe the next day, and teach you a little bit more.